Hello, good morning, Dr. Shangeetha.
Hi, good morning, doctor. Can you hear me? Dr. Gallo, can you hear me?
I'm not sure. Can all of you hear me?
I can hear you, Miss.
Can you hear me? Hello?
I can hear you, Dr. Sangi.
Oh,
Miss,
something wrong with my speaker.
Okay, so that means everyone else can hear me, right?
I cannot seem to hear anyone. Sorry.
Yes, doctor, we can hear you, and Dr. Gallo too.
Okay, I can hear Barik. Yes. But I'm not sure whether Dr. Gallo can hear me. Okay, hi everyone. I hope you can hear me. Not sure if Dr. Gallo is still here. Maybe she has yeah, she's here. Okay, so today we have a large number of influx of students. Okay, so I heard that the class has been open to everyone. Okay, but we actually already done with the some parts on the introduction to the class, right? So how I will go about the class is usually there will be a pop quiz before the class starts, based on whatever that was learned in the last lesson. Okay, so I see that the number of students are still increasing. So for students who have registered for the course, I would like to ask you to give extra attention, especially when we are doing the pub quizzes and also the assignments and so on, right? So my classes are always, there's always activities in the class. So especially for the students who are registered, it's very important that you follow closely, because your test will be based on the activities and so on. So it will be very important to understand what we are doing, right? So as per the last class also, we will have breakout rooms when we do the activities, so that it will be easier for me to coach you in a smaller group, okay? But I'm not sure, our group might not be as small as last week, but I will try my best to coach you with some of the questions. And I hope the group work will not take too long, because the number of students are 17, I see. Yeah? Okay, so without further ado, all right, so let's start the class with a top quiz that I told you about. Okay, let me just check on it. Okay, so I want you to what do you call? I don't know whether all of you are familiar with Kahoot. Okay, so you can go into Kahoot, right? Okay, and do you know how to go to Kahoot? Right? Can you see my screen?
Yes.
Yes, doctor.
Have you all played Kahoot before?
Yes, doctor. Yes.
Yes,
Yes.
doctor.
Okay, then it's great. So you guys can what do you call use your handphone, all right, to go into Kahoot. Okay, www.kahoot.it. Okay, and key in the game pin. All right. Okay. Okay, so we have about 56 students. I hope from the 56 students, especially those who are, registered students, make sure that you are in. Okay, 57. Okay, registered students, it's compulsory for you to be in. All right, the other students, you can either watch or you can join in if you want to. Okay, it will be regarding the, lesson from last week. Okay, all right, 58. All right, so I'm going to start now. I think I better lock the class. One more student and I will lock the game. All right, and we can start. Okay, because there's too many students, then it might take too long. We have to start with class, right? Okay, I shall, all right, 60 students, I will lock the game and we can start. Okay, all right. Okay, quickly answer. You're almost running out of time. 5 more seconds. Okay, all right. So the process to determine how to overcome energy barrier to transform from reactant to product is kinetics. All right, that's the answer. Okay, now I hope that you remember from last week, and I hope the 30 person who answered correctly came from the class who attended last week. All right, so last week we had 35 students. I hope 30 out of 35 who got it correct are from my class. All right, okay. Music. Okay, so next question. So let's see the scoreboard. Super Panther got 931. Okay, so you are the fastest to answer the correct answer. Okay. All right, let's go to the next question. Okay. All right, so only 28 of you got it correct. So direction of spontaneous change, the process will be thermodynamics. Okay, thermodynamics only tells you it moves from a reactant to the product. Okay, it only tells you the direction. Okay. Now, let's see how many of you. Super Panther again. All right. I'm not sure who's Wing Pony. Okay, you are the second after Super Panther. Right. Up by 18 places is Amazing Wallaby. Okay, you are the highest climber. All right, let's see the next question. Okay, what does kinetics tell you? Okay, so actually for this question, we have 3 correct answers. Okay, those who answered transformation between phases, only the crystalline structure changes, all right, or the atomic arrangement. Okay, as we said, there's going to be breaking of bonds and formation of new bonds when your reactant changes into your product. Okay, and also your chemical composition will remain the same. All right, okay, so let's see next. Again, Super Panther and Hero Cola has the highest answer, streak of 3. Okay. Next question. Okay, so the correct answer is, again, there is two answers. Okay, it is acting as a catalyst in order to lower the activation energy. Okay, good. High number of students actually answered correctly. Okay, so you can answer either one and you are right. Oh no, winged pony actually overtook Panther just now, right? Okay, very good. Winged pony. Okay, next question. Okay, so this was actually a bonus question. So what are the factors that affects the rate of reaction? Physical state of the reactant, the temperature of the reaction, the concentration of the reactant, and the presence or absence of catalyst. All the answers are correct. Okay, so I hope you had fun. Huh? Let's see who. Helpful giraffe is number 3. Smooth dolphin got number 2. And number 1, the first place, goes to winged pony. Okay, so winged pony got number 1. All right. Okay, so that is for the game that we want to do today. Okay. Okay. So, all right. Okay. So I hope you had fun and also, managed to help you to remember back what we learned last week, right? So today we will go into continuation of the notes. Before that, I want to say that thank you to Barik for helping me to do the arrangement in the Padlet, right? So, and also I saw the PDFs that was, the presentation that you guys have prepared for the, the changes between the diamond and graphite, right? And all of you did it very nicely. So you can go and download and also look at each other's work. Okay, now let's go into today's lecture, which is a continuation. Okay, now, so last week what you have learned is you learned how to differentiate between thermodynamics reaction and also kinetics reaction. And to give you a little introduction into what is kinetics, okay, and what are the important things that you need to know in order to study about kinetics. Okay, now today's lesson we will go deeper into understanding how are you going to measure and also the techniques that are involved in your kinetics study. Okay, so there is something called the empirical kinetics. Okay, so which means when we say empirical, that means the numbers becomes very important. Okay, so all right, imagine you are writing an equation. Okay, an equation for a reaction, right? Do you just write the equation based on the types of the compounds that you put in, or do you need to balance your equation? Okay, so as a chemist, you should know that whenever you write an equation or a chemical equation, you need to balance the reactants and the product. So this is where it is known as stoichiometry of the reaction. Okay, so when you want to do a study of kinetics, the stoichiometry of the reaction and also any other side reaction that might have happened needs to be identified. Because remember, by studying kinetics of the reaction, you can actually determine the the mechanism of how your reactants has changed into product. Okay, so that's where the stoichiometry becomes important. So let's say you have in your reaction mixture, you have 5 carbon and maybe 10 hydrogens and maybe 2 oxygens. All right. But in your reactant, suddenly you have chlorine. Okay. Sorry, in your product, suddenly you have chlorine being produced. Okay. So that means there is something else that has happened in the reaction mechanism. Okay, maybe there is a contamination somewhere, right? So those are the meaning of site reaction. So all these need to be studied in detail in order for you to get data for the study of kinetics. Okay, so whatever that you put in is what you must get in the end in your products. Okay, so when that happens, right, you need to be sure, okay, or you need to study the concentration of your reactants. What are the things that you are putting into your reaction mixture? All right, and then you need to study the concentrations of the products that are being formed, right? So when you put the reactants, what are the things that are being formed and the concentration of the products, okay? And of course, you need to determine how long is your reaction is taking place. So this is very important because as we said from day one, right, we are studying rate of reaction. Okay, we want to know what happened within a set stipulated time frame. Okay, and of course, temperature difference will play a role. Okay, we will look at that later. All right, now, so what happens if your reactants are in the gas phase? Okay, or your products are in the gas phase. Okay, so when that happens, the pressure and also the volume of the gas will become important. Okay, or sometimes the pressure can remain constant, but the volume will change, right? So you need to measure the volume. Okay, and if let's say your reactant or your product it is in liquid form, okay, also it becomes different. Maybe you can measure the concentration, right? Okay, now what happens if your product that is being formed is in solid phase? Okay, maybe when you add 2 liquids together, it actually forms solid in the end. Okay, insoluble solid in the end. So how do you measure that? Okay, so different phases will have different requirements in terms of the measurements to collect data for your study of your kinetics. Okay, all right. Now, so how are we going to study? Right, so that's what we're going to be looking at now. All right, now, if at least one of your reactant is in the gas phase, there will be a change in the gas pressure as the reaction progresses at constant volume. Okay, so if your volume is constant and then suddenly you have gas inside. Okay, so if it is starting to progress, if let's say initially it was in gas phase and then in your product you no longer have the gas, right? Maybe already changed to liquid, okay, or so on. So there is going to be a change in the pressure of your reaction, okay? Now, another way to monitor will be, other than pressure, of course, is if your reactants or your product have color, okay? Then you can use spectrophotometry, okay? If let's say whatever reactants or products that you're forming or reactants that are reacting produces color. Okay, so you can use spectrophotometry because it has absorption of radiation in the spectral region. Okay, so let's take for example hydrogen and bromine gas. Okay, so hydrogen is a colorless gas, right? And then you have bromine, which has a slight amber brownish yellow coloring. Okay, and then you produce your HBr, which is a colorless gas. So when you mix these two gases together, right, and then you have the color being formed, and as the reaction progresses, the color will disappear. Okay, so you can actually measure, right, the absorption of visible light by bromine. Okay, that is one way to monitor the progress of the reaction when there is color involved. Okay, now another example you can do is to monitor the electrical conductivity of the solution. Okay, if let's say you're using, like for example here, Okay, as you can see in this equation, the reactants are neutral molecules. Okay, but when you add these reactants together and you allow them to react, it actually forms H plus and Cl negative ions. All right, so when that happens, all right, in your product, there's going to be a change in conductivity. And because you have hydrogen ion being formed in your product, you can monitor your reaction, your rate of reaction, using a change in the pH. Okay, you use pH meter and you can monitor the change in the pH of your solution as the reaction progresses. Right? Okay. Now, other methods, you can have GC, you can have MS, you can have NMR, and so on. Okay, so these are certain instrumentations that you can use in order to monitor the progress of the reaction, all right, and that you are performing. Okay, now this is a new slide. It might not be inside your notes. Okay, so don't worry about it. I will upload this slide into the Padlet, right? Okay, what do you call? This is another technique, okay, of what do you call, monitoring the progress of the reaction. Okay, it's actually a very common technique that can be used, especially when you're using reactants in the gas phase. All right. Okay. So what will happen is, so you can have a mixing chamber with two different inlets. Okay. So because they have two different inlets, you can actually run two different types of gases to pass through the inlets. Okay, and then it goes into the mixing chamber. So you can see here I've used two different colors to show the difference that actually you're using two different types of gases. Okay, and then when they go into the mixing chamber, so they turn into different color. Let's say in this instance, for example, it turns into pink color. So let's assume that pink color is probably the intermediate product, all right? And as the reaction progresses and as the gas moves, as the mixture of gas moves through the chamber, all right, you have the detector that can move along this, what do you call this tube here, and it can detect what are the products are being formed throughout the reaction. So this is a continuous flow technique, okay, where the detector will be able to detect along the chamber, okay, what are the products are being formed throughout the reaction, okay. Now, another technique will be to, similarly, it's known as a stop flow technique, where at the end here, another syringe will be attached to stop from it moving out. Okay, so when that happens, your detector will be allowed to be static. Okay, so which means when the reaction progresses, the detector only measures at one point. Okay, that is the stop flow technique. So that means only at the end. Okay, right? So that is another technique to measure or monitor the progress of your reaction, to collect data in order for you to to get enough data to calculate your rate of reaction and so on, okay, or to monitor the progress of the reaction. Okay, now let me share with you one video, right? Hold on, let me stop for a while and I'm going to share one video with you. I hope I'm not talking too fast, huh? Okay, give me a few seconds on the video and share. Okay. So I think you can see it. Just let me just adjust the volume a little bit. All right. So let's watch this video.
In this video, you're going to learn what reaction rate is, as well as some ways of measuring reaction rate. So your first question is, what is reaction rate? Reaction rate is the measure of how quickly the reactants in a reaction change into the products of the reaction. Now let's look at how you can measure reaction rate. The rate of a chemical reaction can be measured in two ways. The first way is to measure how quickly the reactants, that's the substances on the left of the arrow in the equation, decrease. The second way is to measure how quickly the products, that's the substances on the right of the arrow in the equation, increase. Looking at an example for each of these two methods will help you understand this. Our example for way 1, measuring how quickly reactants decrease, is a reaction between marble chips, calcium carbonate, and hydrochloric acid. This reaction can be represented by the following equation, made up by the reactants calcium carbonate and hydrochloric acid, resulting in the products calcium chloride and water and carbon dioxide. As the reaction proceeds, the reactants lose mass because carbon dioxide gas is given off. We can measure the decrease in mass of reactants by using this type of apparatus. Based on our measurements, we plot a graph of mass of reactants against time, which looks like this. The rate of reaction at point A is given by the gradient at A, which is y over x. And the rate of reaction at point B is given by the gradient at point B, which is y dash over x dash. What do you think is happening to the rate of reaction as it proceeds? Pause the video here, give it a think. The answer is that the rate of reaction slows down. In other words, the rate decreases. Did you get it right? Do you remember there's another method we mentioned earlier? Consider the same reaction. Instead of measuring the loss of mass of the reactant, we can measure the gain in volume of the product, carbon dioxide, using an apparatus like this. You can watch our video on measuring the volume of gases here. This time, we plot a graph of volume of gas produced against time. The graph looks like this. As before, the rate of reaction at point A is given by the gradient at A, which is y over x. And the rate of the reaction at B is given by the gradient at point B, which is y dash over x dash. What do you think is happening to the rate of reaction as it proceeds? Again, pause here and try to get the answer. As in the other test, it slows down. The rate of reaction decreases. So let's recap. The rate of reaction is a measure of how quickly the reactants change into the products. The rate of reaction can be measured by measuring how quickly the reactants decrease or how quickly the products are formed. The rate of reaction usually decreases as the reaction proceeds.
Okay, so this video was actually taken from Fuse School. All right, I'm sharing it from Fuse School. So you can also go and search for it on YouTube and you can watch it. All right, okay. So the reason for sharing is to give you a little bit of visualization of what I have been talking for the last maybe 10 or 15 minutes or so. Okay, so how the reaction progresses and what are the things that you can measure in order for you to have enough data to know how fast your reaction is progressing or how slow it is progressing. Okay, so as in the point of view of reactant as well as in the point of view of products. Okay, so let's continue with the lecture notes. All right. Okay, so now, so let's go a little bit into the experimental techniques itself when it is involving gases. Okay, so here is one question, right? I will explain first on the question and then and also the answer, and we will break into groups and we will see and I will go in to assist the groups, the smaller groups, to see if you have any questions or if you don't understand, because there will also be another question similar that you need to answer. Okay, so here it is already being explained, but I will explain to you how to do it. Okay, predict how the total pressure varies during the gas phase decomposition of 2N2O5 into 4NO2 and oxygen in a constant volume container. Okay, so you want to predict how is the total pressure once the your reactant has decomposed into two different types of gases. Okay, so in order to understand this question, the method is, right, the total pressure at constant volume and temperature and assuming the perfect gas behavior is proportional to the number of gas phase molecules. Okay, you have to understand this. All right, so that means the total number of pressure in the end, all right, will be proportional to the number of gas phase molecules. Okay, so from here, okay, because each mole of N2O5 give rise to 5/2 mole of gas molecule. Okay, why? Right, so if you see the balance equation here, okay, you have 2N2O5 producing 4NO2 and 1O2. That is the ratio. Okay, so if you have 1 mole of this, that means your total number of gas molecules will be 5, because there is 5NO2 and 1O2 will be produced when you have 2. So that means 5/2 mole of gas molecules. All right. And we can expect the pressure to also rise 5/2 times the initial value, because the total pressure is proportional to the number of gas molecule. Okay. Now, so how to answer the question? All right. We will let the initial pressure to be PO and the initial amount of N2O5 molecules present to be N. Okay, remember, this is the stoichiometric ratio. So that means for every 1 N2O5, you will be producing 2 NO2 and half O2. Okay, the stoichiometric ratio is as such based on the balance equation. So now assume that you don't know how many number of molecules of N2O5 is present, which is N. Okay, so when a fraction of alpha, this is alpha, of the N2O5 molecules has decomposed, right? So now we are talking in terms of fraction. Okay, so a full fraction is 1. Okay, so when your N2O5 start to decompose in the reaction mixture, so a fraction of it, or alpha fraction of it, is being decomposed, okay, to form NO2 and O2. Okay, so that's why it is 1 minus alpha. All right, and then you have 2 here, because for every 1, it is 2 in terms of ratio NO2. Okay, and of course you have to times by the fraction that is being formed. All right, and times by the number of molecules. Okay, now then your oxygen is half the fraction times the number of molecule. Now, if you now try to add N 1 minus alpha plus 2 alpha N plus half alpha N, you will find that you will be able to get N 1 plus 3 over 2 alpha. Okay, so when your alpha is equals to 0, the pressure is PO. Okay, that means at the start when your fraction is 0, so that means your reactant is still full. Okay, so your pressure is PO. So at any stage, the total pressure is 1 plus 3 over 2 alpha times by PO. Okay, so when the reaction is complete, the pressure would have risen to 5 over 2 times the initial value. Okay, which means assuming that it is 1. Okay, assuming that alpha is 1, then you will find that the pressure at completion is 1 plus 3 over 2. Okay, so that is the equation for the pressure, the prediction for the total pressure at the end of reaction. Okay, now what I will want you to do next in your group is to repeat the calculation for 2NOBr in order to get 2NO plus Br2. Okay, can all right. So I think I will need Dr. Gallo's help to break down our participants. Dr. Gallo, can you hear me?
Yes, can you hear me, Doctor?
Yes, can, Doctor.
Okay, good. So I have a problem with my speaker previously, so I think it's solved now. So I will open the breakout rooms, but for the students registered to this class, I will ask you to take a breakout room 1 to how many breakout rooms, Doctor, we need for the registered student?
I think for registered students we can take 5 groups. 7
groups.
Yeah, 7 in each group.
Okay, so each group contains 7 students. So we'll have 7 students. So then I will have 10 breakout rooms. I will have 10 breakout rooms for those of you who are registered students. Please take group 1 to 5. Okay, take group 1 to 5, and then other students can take group 6 to 10. Okay, can you understand the group breakout? Okay, I hope you can get that. So I will let all of you to choose your own room. Just keep in mind each rooms will have 7 students, and then registered student choose group 1 to 5. Okay. Okay. Have you got the invitation?
Yes, Doctor.
Okay, good. Ya, silakan ya. Jadi mahasiswa-mahasiswa yang registered di perkuliahan ini, yang memang mengontrak perkuliahan ini dapat mengambil grup 1 sampai 5. Masing-masing grupnya 7 orang. Kemudian peserta lainnya yang sit-in atau yang mengambil kuliah ini dari undangan boleh mengambil grup 6 sampai 10 ya. Silakan bisa langsung saja masuk ke breakout room. Okay, I think we have some students already go to their rooms, Dr. Sangi.
Okay, Doctor.
So you can actually go to any rooms that you want as host. So yeah, you can try later after all of the students go to their rooms.
Yeah, sure. Group 4 seems to have 1, 2, 3, 4, 5, 6, 7, 8, 9. So maybe 2 from group 4, room 4, can you move to other room? Either room 3 or room 2?
I think we need to ask the host to do that.
Because room 5 is empty.
Oh, room 5 is empty. Yeah.
Okay, I will just
yeah.
randomly. I just randomly put lah.
Okay, okay, good. Thank you, doctor.
Sorry, doctor, I
Yeah.
cannot join the breakout room because I'm joining Zoom from handphone.
That's fine. That's fine. Yeah. For those of you who cannot go to the breakout room, are you registered student?
Yes, doctor.
Oh.
May
Kenapa
you
nggak bisa ya?
add me? Nggak bisa, Bu Galuh.
Siapa namanya?
Rahmadanti Widya, Ibu. Boleh izin ke grup 2 tidak, Bu?
Oh, sebentar ya. Oke, grup
Oke,
2
baik.
udah penuh ya. Saya masukin ke grup 4 aja ya.
Oh iya. Oke, baik Ibu.
Sudah
Terima
ada
kasih,
yang
Ibu.
ya, silakan di gitu.
Dr. Kalu, I'm not sure whether all in group 1 to 5 are our current registered students, because seems like there's too many students in there. I think there might be some who are not registered students who are also inside there. So I hope all the registered students are in the group 1 to 5. Because I don't want them to miss out.
Yeah.
Maybe I just broadcast a message.
Okay. Yeah. Group 1 is currently have 6 students.
Yeah.
Group 2, room 2 has like 7. 1, 2, 3, 4, 5, 6, 7. Oh, 8. Group 2 have 8, right? I think group 3 has too many students here. Group 8 is empty, so yeah, because they're already in their breakout rooms, they cannot actually hear us. So probably we can just go to the rooms now.
Yeah. I was just broadcast a message to all the rooms.
Okay, yeah.
Let me just tell them, non-registered students, please. Okay, so I will just go into group by group and check on them. Right.
Assalamualaikum Bu Galuh.
Waalaikumsalam. Siapa ini? Rahmadanti? Ya,
Ya, Ibu, maaf.
Rahmadanti.
Tadi saya sudah join ke grup 4, Ibu. Tapi tiba-tiba saya pindah ke grup 8, Ibu.
Rahmadanti itu ya, register ya?
Iya,
Bisa itu lagi nggak? Bisa, oh iya. Tapi di sini belum ada namanya Rahmadanti, belum bisa di sebentar ya. Coba saya bisa. Rahmadanti, room 4. Nggak ada ya. Kamu sekarang di room 8 ya?
Iya,
Registernya
tadi
di room
saya kepindah ke room 8, terus saya leave breakout room, Bu.
Ya, kamu sekarang saya masukkan ke room 2 aja ya.
Oke, Ibu.
Ya, silakan.
Terima kasih, Ibu.
Ya. Di sini siapa yang belum nih? Naura belum masuk room.
Ibu saya belum masuk, Bu. Tadi kelempar Zoom-nya.
Amanda mau room berapa? Amanda mau masuk room berapa?
Room 2 aja deh.
Register tidak? Amanda register tidak? Mahasiswa yang mengontrak kuliah ini bukan?
Iya, Ibu.
Iya, oke. Kalau iya berarti saya masukkan ke grup 2 ya.
Baik, Ibu.
Sudah ada undangannya?
Okay, we shall wait for the rest of the members to be in. Okay, for group 1 to 5, you guys can prepare your answer to be presented now. Okay, then you can take a look at it. I hope I've explained it clearly. Yeah. So mostly the questions were some couldn't understand why half of oxygen. Yeah. Right. Okay. So some were asking why half here for oxygen. Okay. It's because here is 2. Okay. 4 to 1. Correct. Okay, so if I reduce it to 1, this becomes 2. Okay, and this becomes half. That's what it means. Okay, so another popular question that everyone was, not everyone, some of you couldn't understand is the meaning of alpha. Okay, so I used one analogy to explain. Okay, so you imagine you have one piece of apple in your hand. Okay. So this is for those who still don't understand. Those who already understand, it's okay. Okay, so you have one piece of apple and you took one bite from the apple. Okay, let's say you took one bite from your apple in your hand. Okay, so you have one apple initially. Now you took one bite out of your apple, which is your alpha. How many apple do you have now? What happens to your apple? Your apple now is 1 minus the alpha fraction that you have already eaten off. Okay, so that's why as your reaction progresses, your N2O5 becomes 1 minus alpha. Because from 1, it is reducing as the reaction progresses. But what happened to the alpha? The alpha changes into your products. Okay, and how much of the fraction depends on the stoichiometry of the products, which is 2.5. That's why you must times 2 and times by half. Okay, so if you add all together, okay, you will be able to get the total amount. Okay, so that is from me. Now let's listen from group. Let's try group 5 first. Okay, because they already wrote the answer on their screen when I went into the group just now. Okay, so and they got the answer correct. All right, so let's have group 5 to share your screen. Okay, and maybe you can explain to everyone because you guys already understood by the time I reach your group. Okay. Group 5, can we have one person to share and perhaps explain to the class?
Doctor.
Yes, hi. Okay, group 5, I can't see your answer anymore. Where is your answer? Just now it was there. It is correct. Just need someone to, explain to everybody. You got the answer right? Okay, go ahead, explain it. You can show the other one just now, actually, the Word document. That's good with the explanation and everything. Okay.
Okay, can I speak in Bahasa, Dokter?
Can. I will try my best to understand. Should be okay,
Oke. Kan di sini tuh ada 2 NOBR menjadi 2 NO plus BR2 ya harusnya. Nah, terus dibagi 2 disamaratakan jadinya itu NOBR menjadi NO plus setengah BR. Nah, kan NO-BR-nya itu udah 1, berarti NO-nya itu 1 dan BR-nya itu setengah. Lalu diubahlah jadinya N dikali 1 min A, lalu yang NO-nya itu AN ditambah setengah AN. Nah, terus N-nya itu dikalikan dalam kurungnya, jadi N dikurang AN, lalu ditambahkan AN ditambah setengah AN, sehingga totalnya itu menjadi N ditambah setengah AN, lalu N-nya itu dikeluarin, jadinya tuh N ditambah 1 ditambah setengah A. Nah, tinggal dimasukin ke yang tekanannya itu dirubah, jadinya tuh P sama dengan 1 ditambah setengah A dikali P0. Seperti itu.
Okay, how about when your alpha becomes 1? That means at the end of the reaction. So it increased by how many times? Tadi itu dalam your Word document tu dah betul. This is correct. Your answer is correct. But the last part is missing. So increase by how many times? That means when you assume alpha is 1, so increase by how many times?
3/2.
Yes, 3/2. So if your alpha become 1, okay, that means at the end of reaction, your alpha become 1, correct? You finish already, okay? The fraction will become 1. So when that becomes 1, is 1 plus half, okay? So the pressure is 3/2 the initial pressure, okay? Okay, all right. So anyone else? Okay, group 5, you can stop your, what do you call? Can we have one more group to present? Maybe we can have one group to present in English. Present your answer. Maybe either group 1, maybe. Can we have group 1? Then we can proceed with the lecture for a while. Come on, group 1.
Group 1, Doctor?
Yeah. Can you do it?
Okay, all right. Melinda, can you share screen?
Okay.
Okay. Can quickly explain it? Barak, maybe?
I will explain with Melinda.
Yeah, sure.
Okay.
All right.
So the question that you asked, that to do the same thing like the example is, in here there is 2 nitrosyl bromide, sorry, and the product is nitro and bromide. So the nitrosyl bromide have 1 constanta, and the product is nitro have 1 and the bromide have an half, because there's 2, and in nitro is 2 and bromide have 1. So just like divide by 2, you can have 1 and 1.5 and 1/2 1.5, sorry, for the ratio. After that, you're doing the same thing like you example by like the piece of apple that you bite some part of them. Then you have this equation, n multiplied by 1 minus alpha for the reactant, because the reactant it will be decreased, and there's the product is, and the alpha will be into product. So here we have alpha, 1 alpha, and in bromide we have half alpha. Okay, so we total we doing the same thing like previous group. We have this total, this n multiplied by 1 plus half alpha. Can you explain the next, Melinda?
All right. Thank you, Barik. So after that, let's say the alpha is 0, so the pressure will be in here below the equation 1 plus a half alpha multiplied by initial pressure. And so the conclusion is when the reaction is complete, the pressure will have risen to 3 times its initial volume. Thank you.
Okay, so when the reaction is complete, your alpha actually becomes 1. All right, so that means it's completely consumed the reactant. Okay, so your alpha becomes 1. Okay, so that's why the final pressure will be 3.2 times the initial pressure PO. Okay, all right. Thank you. You can stop the sharing now. All right. Okay. Now, so let's go a little bit into notes a little bit more. Okay. All right. Just proceed first. All right. So I hope that was helpful to help you guys to understand a little bit on why you need to monitor the progress of the reaction and how the reaction actually proceeds. Okay. So next, we want to go into the definition of your rate of reaction itself. Okay, so from whatever that you have learned so far, okay, you probably now you understand the importance of knowing how much of reactant there is at each time in your reaction mixture and how much of product is being produced at each time. Okay, so the change in the concentration of reactant or product per unit time, you can actually represent them 3 ways. Okay, firstly, it can be in terms of average rate. Okay, so average rate basically means, let's say you want to find the reaction or the rate of the reaction in a certain time period. Okay, let's say 120 seconds. Okay, so average rate is the change in your concentration within that 120 seconds. Okay, now that means from the start of the reaction until the end of the reaction. Now, instantaneous rate means at any point, let's say in that 120 seconds, you want to find the rate of reaction at 20 seconds. And then you want to find the rate of reaction at 40 seconds. And then at 60 seconds. And then at 80 seconds. Right? So at this particular second that you are specifically interested in finding are the instantaneous rate. Okay, and the third type is the initial rate. Okay, initial rate is basically the instantaneous rate at time equals to 0. Okay, so initial rate is actually the instantaneous rate at time equals to 0. Okay, so we will go into individual rate to explain how you want to find and so on. Okay, but before I forget, for next week class, we will perhaps next week, maybe if we have time, let's see how much we finish today and how much we will do next week. But you can start to download Graphmatica, okay, and also have your Excel ready, all right, for the following classes, because we will do some graph, we will plot some graphs, and we also will determine from the graph how to, we will learn how to determine your rate of reaction from the graph of concentration versus time. Okay, so for next week class onwards, download Graphmatica and also make sure that you have a working Excel in your computer. Okay, all right. Now, to continue for today's lesson, so for example, when you have a reaction, okay, where you have your reactant A that changes into product B, okay, so the average rate of appearance of B is actually the change of the concentration of B from the start of reaction until the end. So at the start of reaction, your B will not be there, correct? Because you just only put in together, so that is at initial, okay? So you haven't had time for your B to start forming, okay? Then over the change in time or the differential in time, all right? So later on, we will go into the concept of the differential. We will see how much we will go into today, all right? So average rate of appearance of B is change in concentration of B over the change in time, all right? Okay, so to put that into perspective, let's say you have a round bottom flask, okay, containing gas A, right? So you can see here at time 0, you have a round bottom flask with what do you call gas A, which is black in color. Okay, so let's say the number of mole of A in this round bottom flask is 1 mole. So at time 0, your number of mole of B is 0. Okay, at time 0, the number of mole of A is 1 and number of mole of B is 0. Then 20 seconds later, you measure and you found out that your A has reduced to 0.54 and your B has increased to 0.46 mole. All right, so in 20 seconds, your mole of A has reacted and reduced in amount to 0.54 and your B has formed 0.46 mole. All right, and at 40 seconds, then you let it react again and then you check again at 40 seconds. And at 40 seconds, you find that your mole of A has further decreased to 0.3 mole and your mole of B has increased to 0.7 mole. Okay, so this rate is a change in the concentration over a period of time. So that means just now, okay, in the earlier slide, we were talking about the appearance of B, right? So from here, you can see your B has gone from 0 to 0.46 to 0.7. Okay, so that is the change in the concentration of B over 40 seconds. Okay, and this doesn't only work for the concentration of B, you can also explain it for the concentration of A. Okay, so the concentration of A has actually decreased over time, while the concentration of B has increased over time. Okay, so that is what rate is all about. Is the differential in the concentration over the differential in time. Okay, the difference in time. Okay, now let's go into one very short what do you call calculation to understand better. Okay, now let's say you have this reaction, okay, C4H9Cl, all right, in aqueous form, right, it's added to your H2O, which is liquid, right, to produce your product, okay, which is C4H9OH and HCl. Okay, for the reaction, okay, earlier we learned that for the reaction for A to change into B, right, we are talking about the rate of appearance of B, the change of concentration in B over time. Okay, now here the data that is given to you is they have taken the concentration of the product at every 50 seconds initially, okay, then 100 seconds, then at 100 seconds, every 100 seconds, finally 800 seconds. That means after 300 seconds. And they have monitored the decrease in the concentration of the reactants over 800 seconds. Okay, all right. So they have found that at each time they measure the concentration, it is decreasing. Okay, so from here, what information can you get? Okay, now you can get a lot of information from just that 2 data set, actually, right? So you can actually, right? So this is the manual calculation. Okay, of course, if you straight away plug in the data into a graph, which we will learn next week, you can immediately find the concentration, find the rate from the graph, okay? But in order to understand what is exactly happening, okay, this is how to explain, right? So at time 0, your concentration of your reactant is 0.1, okay? So there is no change in the concentration of your C4H9Cl, right? And at time 50 seconds, okay, after 50 seconds, when they measure, they found that the concentration has reduced to 0.0905. Okay? So how much the change actually? Okay, so you take 0.1 and you minus 0.0905. Okay, and then you will get your change in 50 seconds. Your concentration of A changed reduced 0.009050. Okay, that means in 50 seconds, this amount has reduced. Okay, in 50 seconds. Okay, so average rate is basically you take the change in the concentration, you divide by the amount of stipulated time. Okay, so at that, from 0 to 50, the average rate is 0.000181. Okay, but like I said, now it's just to show you manually how it works. Okay, next week when we learn how to plot the graph, you will understand better when, or maybe today's lesson is important for you to understand what actually happens in the graph. Okay, so this is the manual way of looking at it. Okay, so you can do the same. Okay, you can try to calculate. Okay, take out your calculator and then you minus and see whether all these values are correct and what happens when you take this and you divide with the change in time. Okay, then you'll be able to get the average rate. Okay, but what is the thing that I want to draw your attention to is the last part here. Okay, look at all these values. Okay, now let me just remind you that, okay, let me see, just give me 1 minute. Okay, right, so we are only talking about the reactants here. Okay, the change in the concentration of the reactant here. Okay, so you can see that, right, as the reaction progresses, okay, it is actually decreasing. Okay, the average rate is actually decreasing as the reaction progresses. Okay, that means, can you imagine, you start eating the apple just now, all right? And towards the end of finishing your apple, you're no longer hungry, okay? Because your apple becoming smaller and smaller. So the rate as how fast you're eating your apple becomes slower because there's no more apple to eat, okay? Basically, that's what it is. Your reactant is starting to finish, okay? As the reaction is progressing, your reactant is starting to finish. So the rate will actually slow down as the reaction progresses. Because why? There are lesser collision. Okay, so there is lesser collision between the, sorry, I'm trying to use the pen. Okay, so there is lesser collision between the reactant molecules. Okay, because as your reaction progresses, the concentration of your reactant decreases. Okay, so that means you have less reactant to form product. Okay, that's why your rate also will decrease as the time progresses. Okay, right? I hope you can understand that, huh? Right? Okay. So, hold on. I don't know why annotation is still there. Okay, that's funny. Give me a few seconds. Let me just delete the annotation. That's from the previous page. Huh? Not sure why is it appearing still. Sorry for that. Huh? Okay. So when you actually, just now we said, right, what we did was to calculate manually, okay, to know what is exactly happening at each point. So you can actually just take the two data here, and you can actually plot the graph of concentration versus time. Okay, so when you plot the graph of concentration versus time, you will find that you get a graph that looks like this, which is correct, okay, because when we calculated manually, we also saw that the rate is actually decreasing. Okay, so when you see the graph, you will see the graph is actually decreasing. Okay, now I just want to quickly explain a little bit on the graph, but don't worry if you find it hard to understand now, because next week we will start back from here and I will explain in more detail, and we will try to calculate and see the difference in the rate in certain points in the graph. Okay, so don't worry about it now. Let's just look at the initial rate and also the instantaneous rate. Okay, so initial rate, as we said earlier, okay, it is actually instantaneous rate at time equals to 0. Okay, so that means at time 0, okay, this is your initial rate. Okay, so in order to calculate, you will actually draw a tangent and then you calculate the difference in the concentration over time. Okay, so once you're able to draw it later when we learn Graphmatica, okay, we will be able to calculate from the tangent line. Okay, or you can draw it manually on a graph paper also. Okay, if you would like to do a manual graph, you can actually plot it in a graph paper and you can draw the tangent and you can also calculate. Okay, but we will try with Graphmatica next week. Okay, so next is instantaneous rate at time t. Okay, so at any point in the graph, you can actually calculate the rate of reaction. Okay, you only need to be able to draw a tangent. As long as you can draw a tangent at the point, you can get the difference in the concentration over the difference in time. So here, for example, we have drawn at 500 seconds. Okay, then when you take the when you calculate the slope of the tangent, then you'll be able to tell the rate. Now, the important thing that I want to draw your attention to today before we end the class is, right, going back to what we saw earlier, okay, this reaction here, okay, so your reactant is C4H9Cl plus H2O to produce C4H9OH, okay, so the rate for your reactant actually decreases. Okay, your reactant, the rate decreases. Okay, so because the concentration of your reactant decreases, okay, and that is equals to the concentration of your how much of your reactant is being produced, the difference in the products that is being produced. Okay, so negative of the reactant, difference in the reactant over time equals to the difference in your product over time. Okay, so the negative here signifies that rate of disappearance of your reactant, and the positive for your product is rate of production or appearance of your product. Okay, all right, so that means basically you're saying your reactant is being consumed to form your product. Okay, so we will stop here for today. Okay, let me just make a mark. All right, we will stop here for today, and hopefully next week everyone would have your Graphmatica ready so that we can try to plot and find the answer together in your Graphmatica. Okay, all right. So thank you, everyone. Now, if you have any questions, of course, you can always message me, WhatsApp me. And also, oh yeah, before I forget, I want to remind the first 5 groups, please upload the answers just now for the question into your Padlet. Just like always, just put your group name, and also the answer in your Padlet so that everybody will have a chance to take a look at it. Okay, I will check individual individual answers, and if there's any correction, I will just write it in the comments. Okay, all right, thank you.
All right, Doctor. Thank you.
Thank you, Doctor.
Okay, so if you have already signed your attendance, you can leave the group. Thank you. Bye-bye. See you next week.
See you, Doctor.
Thank you, Doctor.
See
See you, Doctor.
Thank you so
Bye.
much.
Goodbye, Miss.